Communication complexity is the study of the amount of communication required to solve computational problems in distributed settings. It falls under the theory of distributed computation. So, in essence, it helps us understand how much information needs to be exchanged when different parts of a system work together to solve a problem. Let us look at the basic communication model. Consider a two-party model, where Alice has an input denoted as X, and Bob has an input denoted as Y. The goal is for them to compute a function f of x and y, written as f of x, y. The main challenge here is to minimize the number of bits they need to communicate to achieve this goal. A communication protocol is defined as a sequence of message exchanges between parties to compute a function collaboratively. First, Alice sends a message, denoted as M1 to Bob. Then Bob sends a message, denoted as M2 to Alice. This exchange continues until the function is computed. Let us discuss deterministic protocols. These protocols have a fixed message sequence, meaning there is no randomness involved. For the same inputs, they always result in the same communication pattern. They require an exact computation. A simple example of this is equality testing. Here, the function q of x, y returns 1 if x equals y, and 0 otherwise. In the protocol, Alice sends x to Bob. Bob then compares x with y, and sends the result back to Alice. Now let's explore randomized protocols. These protocols use random coin flips. They allow for a small error probability, and are often more efficient than deterministic protocols. There are two main types, Monte Carlo and Las Vegas. The advantages of using randomized protocols are reduced communication complexity, a bounded error probability, and the ability to repeat the process for better accuracy. Lower bound techniques are used to prove the minimum amount of communication required for any protocol that solves a given problem. The main techniques used for this purpose are the fooling set method, the rank method, and the discrepancy method. The fooling set method is a technique used to determine a lower bound on the communication complexity of a function. A fooling set is a collection of input pairs, x sub I, y sub I, such that f of x sub I, y sub I equals 1 for all I, and f of x sub I, y sub j equals 0 for all not equal to j. If S is a fooling set for function f, then the communication complexity of f, denoted as C of f, is greater than or equal to log base 2 of the cardinality of S. The matrix rank method is another technique used in communication complexity. We start with the communication matrix, denoted as M sub f, where the rows represent Alice's inputs and the columns represent Bob's inputs. Each entry in the matrix, M sub f of x, y, is equal to f of x, y. The rank of this matrix reveals the complexity of the communication. For any Boolean function f, the communication complexity of f, denoted as C of f, is greater than or equal to log base 2 of the rank of M sub f, where the rank is computed over real numbers. Communication complexity has numerous applications. Some theoretical applications include circuit complexity, streaming algorithms, data structure lower bounds, and proof complexity. Practical applications include distributed computing, network protocols, cryptography, and database query optimization. In summary, some key concepts in communication complexity are communication protocols, the distinction between deterministic and randomized protocols, lower bound analysis, and complexity measures. The analysis techniques used include the fooling set method, the matrix rank method, and the discrepancy method. Communication complexity provides fundamental insights into distributed computation efficiency. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.